Okay, good morning, gang. Looks like folks are arriving. Take 1 or 2 seconds here to get things squared away. Real quick, let's have a look-see here. I think I updated your due dates, but maybe not. Okay, I'll reschedule those. But for now, we need to be using our class time. So, come on, folks. So, good morning, guys. Today is the 28th of September, and this is, of course, a Calc 2 lecture, section 001. If my .cam will stop spazzing out and focus, we can get into it. That looks good. So last Friday, we learned kind of the fundamentals of partial fraction decomposition. We ran through a handful of problems, and I showed you guys the all-important PFD Bible, which tells you how to set up partial fractions for any rational function. Oh, thank you so much, Atanji. That's very sweet. Yeah, we're super excited. Today, I want to show you a few kind of faster ways to go about running partial fraction decomposition. And I'd like to sort of cover a problem or two that walks into the tougher regions, some of the harder examples. So the main things we're going to do today it's all more PFD. I'm going to show you the Heaviside trick. This is also sometimes called the cover-up method. We're going to look at a few examples with repeated factors. Or irreducible quadratic factors. And then, well, I don't think there's really much else planned. So unfortunately, these problems do take a little while, and I think that's about all we'll have time for. So, am I forgetting anything? It's early enough that my brain works about as well as a bowl of soup. So let's go ahead and get started. Let's talk about the Heaviside trick and the cover-up method a little bit, and then we can play with some examples. Really, we should do both at once, because the best way to introduce the Heaviside method is to show you why it works so well with an example. So maybe I'll grab 1 or 2 problems from your homework. Normally, I would ask you guys to tell me what problems you would like to do, but for these purposes, I want to have a little more control. So I'm going to pick an example here. Yeah, let's do number 14. This is homework 5. Y plus 2, 5y minus 1. Okay, I think that's correct, right? Yeah, all right. So here we have a rational function that we're trying to integrate. It is a proper rational function because the degree of the denominator is 2, the degree of the numerator is 1, so I don't need to worry about doing any long division. I'm free to jump in with my partial fractions. My PFD setup will look like this. I step away from the integral. One of the mistakes I see people trying to do is trying to do the partial fractions inside the integral. Of course, that's nonsensical because there's so many steps to the PFD, and they have nothing to do with the calculus operation. So step away from the integral and set up your partial fractions. This is not a difficult example because both of the factors downstairs are simple linear factors, right? There's no power here, and neither of these are irreducible quadratic factors. They're just straight up y plus or minus something. Or here, you know, you could factor a 5 from the bottom to right. This is y minus 1/5 if you wanted, but you can leave it like it is. But still simple linear factors, both of these linear functions, which means that each factor will get one term in the PFD setup. So this is what the PFD setup will look like. And then just like we would normally, I'm going to cross multiply by these two factors to get rid of the denominators. On the left-hand side, I'll just have y, because I'm multiplying both sides by y plus 2 and by 5y minus 1. So over here, both of the factors from the denominator will cancel, just leaving me with the numerator. When I multiply this guy by y plus 2 times 5y minus 1, the y plus 2's will cancel, and I'll just have a times 5y minus 1. When I multiply this guy by y plus 2 times 5y minus 1, the 5y minus 1's will cancel, and I'll just have b times y plus 2. So I want to take a second, make sure everybody's comfy with how we get to here. Are there any questions about why the PFD setup looks like this, or how we arrived at this line? Don't be shy if you do have questions. Hey, Mariana. Exactly, yep. Yeah, so just like when you're solving those rational equations in college algebra, you cross multiply to get rid of the denominators. Doing the same thing. I want to get rid of all the fractions here. So I'm going to multiply by this times this. And I do that everywhere in this expression. So on the left-hand side, when I multiply by y plus 2 times 5 minus 1, both of those factors cancel, and we're just left with y over 1. And over here, one factor will cancel in each of these. The y plus 2 will cancel here. So I'll just have a, the numerator, times the factor that doesn't cancel, 5y minus 1. And over here, when I multiply by y plus 2 times 5y minus 1, the 5y minus 1's cancel, and I'll just be left with the numerator b times y plus 2. All right, the reason I'm pausing here, and the reason I'm happy to stop here for a minute, is because this is actually the line that we're going to use for most of our good stuff when we invoke the Heaviside trick. So the purpose of this example is to teach you the Heaviside trick. You may remember from last week that the next step would be to distribute everything. So I'd have 5a times y minus a here, and then I'd have by plus 2b here. And then I would group my like terms. I'd group the 5ay and by, and I'd group the negative a plus 2b and then I would equate coefficients. That would give me a linear system. We solve the linear system for A and B, and then we can go back and finish the PFD. But the Heaviside trick saves us a lot of time here. Heaviside says, well, shit, this is supposed to be not an equation, but an identity. Does anybody remember the difference between an equation and an identity from their trigonometry classes? Remember, you can hold the space bar to talk, or if you're feeling a little sleepy, you can type in chat. Well, it's certainly true that we're free to do whatever algebraic manipulations we want here, right? I could multiply or divide or add or subtract anything that I wanted as long as I did it to both sides, just like we do with any equation. But that's still true of equations, not just of identities. What makes an identity special, the difference between an identity and an equation, is that an identity is supposed to be true for every number y, for every value of the variable for which the object is defined. So an equation has like a solution, or 2 solutions, or maybe 10 solutions, right? Values of y that would make this equation true, or would make this expression true. But an identity is true for every value of the variable. What that means is I can go plugging shit in for y. That's what makes this nice. I can plug whatever I want in for y here, and the result will be a true expression. Why is that nice? Well, there are some particular values of y that I can plug in that will allow me to just read off A and B. So in particular, this is true for y equals -2 and y equals 1/5. I can plug -2 in for y, and I can plug 1/5 in for y. Yeah, you can plug 0 in also, and there's nothing wrong with plugging in 0. Plugging in 0 can often be a useful move. But the 2 numbers that I'm especially interested in plugging in are the numbers that would make this whole piece go to 0. So I could read off what's left over here, and the numbers that would make this whole piece 0. So I could read off what's left over there. So first, I'm going to plug in y equals -2. Really what I'm doing, I think of it as taking a limit, because this expression up here isn't defined at -2. But after we cross multiply, I get an expression that is defined at -2. So I'm going to send y to -2. So when y is -2, this expression, which I'll call star, so I can just refer back to it. When y is -2, star becomes -2 equals a times 5 times -2 minus 1 plus b times 0, which is excellent news because b times 0 is 0. So I'll get an expression that involves only some numbers and the coefficient a, which means I'll be able to solve it for a. This is -2 equals, what is that? 5 times -2, that's -10. -10 minus 1 is -11. So this is -11 times a. In other words, A is equal to 2 over 11. Isn't that slick? We get the value of A out like immediately. No linear system, right? You may remember from last Friday, the thing that kind of sucks about these problems is that the linear systems that you get at the end can get bigger and bigger and bigger, and they take a minute to solve. They can get so large that you want to fall back on like matrix methods. And I know you guys don't like matrix methods. Even those of you who remember matrix methods probably don't like them very much. So this saves you all of that work. This saves you the whole process of setting up and solving the linear system. I want to pause here and see if everybody is comfy with this. So I'm taking this expression and I'm choosing to plug some values in for y. The values I'm going to choose to plug in for y are the values that make this factor 0. That will allow me to read off this. And then I'm going to plug in whatever makes this factor 0, and that will allow me to read off this. Does everybody see how the expression star here becomes this expression when I plug in -2 for y? The left-hand side here I have y, so that's -2. A times 5y minus 1 is A times 5 times -2 minus 1. And B times y plus 2 is B times -2 plus 2. Well, -2 plus 2 is 0, so that's B times 0. So this goes away. The value that makes the other factor here 0 is 1/5. Nick asks a really good question. So the reason I chose this example rather than letting you guys pick the problem numbers I was going to do is because this doesn't always work. So did everybody see Nick's question in chat? Are there conditions under which this trick won't work? Yes. Yes, there are, unfortunately. But this trick is always useful in the sense that it will allow you to recover some of the coefficients. If you're lucky, it'll allow you to recover all of them. And I'll go into more detail about precisely when the Heaviside trick will get you everything versus when the Heaviside trick will only get you some things. But it's never useless. It's always at least somewhat useful. And in the nicest possible case, it will get you everything. This happens to be the nicest possible case. So if I send y to 1/5, the equation star becomes 1/5, because that's y, equals a times 5 times 1/5 minus 1. 5 times 1/5 is 1. 1 minus 1 is 0. B times 1/5 plus 2. Well, 1/5 plus 2 is the same as 1/5 plus 10/5. So that's 11/5. So I have 1/5 equals 11/5 times B. Which means B has to be, we multiply both sides by the reciprocal of 11/5, and you get 1/11. Ain't that slick? So here we found the coefficients A and B that we need for our partial fractions without ever setting up a linear system. Let's go ahead and finish this problem, and then I'll discuss with you the details of when this will and when this will not work. Remember what my PFD setup was: A over y plus 2 plus B over 5y minus 1. So according to my PFD work, let me just put these up here. A was 2 over 11, and b was 1 over 11. I'll give just a second in case you're still writing, but then I'm gonna cover this up and finish the problem. So this was Heaviside's observation, that I can take this expression that I get after clearing the denominators and plug whatever the fuck I want in for y. It's an important observation because certain values of y make this thing really nice, namely the values of y that make this 0 and the values of y that make this 0. So those are the values that we plug in. Plugging either of those numbers in will allow me to solve for one of the coefficients. So I'm going to bring my paper up here so we can finish the problem. Since I have these now, I can say, okay, therefore, the integral of y over y plus 2 times 5y minus 1 dy is equal to the integral of 2 over 11 over y plus 2 plus 1 over 11 over 5y minus 1 dy. And then we split up the integral. This is 2/11 times the integral of dy over y plus 2 plus 1/11 over the times the integral of dy over 5y minus 1. And each of these integrals is fairly trivial. In the first guy, we make the substitution z equals y plus 2, and dz there is equal to dy, so there's no funny business with the differential. In the second guy, I'll make the substitution w equals 5y minus 1, so dw is 5 dy, which means I'll get a factor of 1/5 out of that integral. And continuing here, this is 2/11 integral dz over z plus, I'll have a 1/5 coming from this piece, and I already have a 1/11 here, so that'll be 1 over 55 times the integral of dw over w. Both of which are natural logs. So this is 2 over 11 times the natural log of the absolute value of z plus 1 over 55 times the natural log of the absolute value of w plus a constant. And then finally, I go back to my original variable. And we're done. So you see this goes much, much, much faster, right? The integrals still require exactly as much work as they did before, but the integrals that we were seeing after doing the PFD were never very hard. Usually just a tiny little u sub, and then a natural log or an arctan or something like that, right? The magic here is all in the algebra. It's all in this Heaviside trick that saved us from having to solve a linear system. Any questions on the steps that came after the partial fractions, on the stuff that's visible on the screen now? Okay. Let's come back here for a minute. Any questions on the PFD itself? So remember at the start, I didn't know this. I just came back and added those values after finding them down here. Not too bad, right? Let's try another example, and this time I'll have less kind of annotation, and I'll just show you what a normal problem like this looks like. Also, in this example, I'll make sure that we don't get everything we want right away. Let's see. Is there just the one of those? No. Okay, there's a few. All right. So I'll do number 16 next, but yeah, sure, what the hell, let's do 16. X squared plus x plus 1 over x plus 1 squared times x plus 2 from 0 to 4. Is it minus 2 or plus 2? It's got to be plus 2, yeah. Okay. So again, the first thing we should check is whether or not this rational function is proper. Remember, that's crucial. If the rational function isn't proper, then you need to do long division. Is this a proper rational function or an improper rational function? It's not always immediately obvious when you look at the thing. The degree of the top is obviously 2, right? Because you've got this x squared. What's the degree of the bottom? Yeah, degree 3 downstairs. So this is proper. Remember, a rational function is proper as long as the bottom's degree is strictly larger than the top's degree. And 3 is strictly larger than 2, or 2 is strictly less than 3. So this is okay. This is good. So we're good to get started. This is a proper rational function. So I can begin my PFD. If this was improper, we would have to long divide, right? And remember, because this is an x plus 1 quantity squared, that's a repeated linear factor. So he's going to get 2 terms in the PFD setup. He'll have something that looks like a over x plus 1, and also something that's like b over x plus 1 squared. And then the x plus 2 term is a simple linear factor, so he'll just get c over x plus 2. You have to remember how to set up the partial fractions. If you don't remember that, then you're dead in the water. So remember, you can get a factor like this downstairs by adding up not just something that has this, but also by adding up something that has this. If I just added these two together, then the denominator would have the factor x plus 1 squared downstairs. So I have to allow for the possibility that there's something like this in the expansion that we're using. So remember, repeated linear factors, you have to build up to that multiplicity. You have to build up to that power. If this was a 3, there would be 3 terms with x plus 1 downstairs. A over x plus 1, b over x plus 1 squared, plus c over x plus 1 cubed, if this were a 3. But it's not, it's a 2, so it just gets these 2 terms, and then the x plus 2 guy here gets this term. I begin the same way. I'm going to cross multiply to kill all of the denominators. My left-hand side, so I multiply both sides by x plus 1 squared times x plus 2. My left-hand side will just be x squared plus x plus 1. On my right-hand side, when I multiply this by x plus 1 squared times x plus 2, one of the x plus 1's will cancel, but nothing else will. So I'll have a times the x plus 1 that doesn't cancel times x plus 2, because that doesn't cancel either. The middle term here, when I multiply this by x plus 1 squared times x plus 2, both of the x plus 1's will cancel. So I'll just have b times x plus 2. And this guy, when I multiply him by x plus 1 squared times x plus 2, the x plus 2 will cancel, but the x plus 1 squared will not. So I'll have c times x plus 1 squared. And this is the equation that I usually like to call, oh shit, fuck my pen, star. The Heaviside trick still has some utility here, but it will not get me all of the coefficients. Because I'm not in that simplest possible case where all the factors downstairs are linear. I have this repeated factor. I have this repeated linear factor. It's not a simple linear factor. And so one of these coefficients I will not be able to get with the Heaviside trick. But I should still use the Heaviside trick to recover as much as I can because it is so very fast. The nice numbers to plug in for x here are whatever numbers will make this 0 or this 0. And what you notice is that if you plug in either of those, this guy is automatically going to be 0. So a is the coefficient that I'm not going to be able to get using the Heaviside trick. But I will show you another trick to get a once you have b and c. So I'm going to use Heaviside. Heaviside sounds like it could be coming from like something heavy, right? But it's not. It's just a dude's name. It's the dude who figured this out. So when x is equal to -1, the equation star becomes 1 squared, -1 squared plus -1 plus 1. Well, -1 squared is 1. 1 plus -1 is 0. 0 plus 1 is 1. So the left-hand side is just 1. What about the right-hand side? A times -1, A times -1 plus 1 is 0, times -1 plus 2 is 1, plus B times -1 plus 2 is +1, plus C times -1 plus 1 squared is 0 squared. And what you notice is that both the A and C terms drop out. This just says 1 equals B. Done. Isn't that slick? So now I've got B. B is 1. If I send x to -2, something nice will happen also. This will drop out, and this will drop out. So it'll allow me to read off C. So at x equals -2, the equation star becomes, let's see, if I plug -2 in here, this is 4 plus -2 plus 1. 4 plus -2 is +2. +2 plus 1 is 3. So my left-hand side is 3. My right-hand side here, this is A times -2 plus 1 is -1 times 0. So this is a times -1 times 0 plus b times -2 plus 2 is 0 plus c times -2 plus 1 is -1 squared. Both of these are 0, so this says c, 3, sorry, is equal to c times -1 squared. -1 squared is 1. So c is equal to 3. And it comes just that easily. Questions so far? So this is what your usual workflow for a problem like this will look like. You'll set up your PFD, you'll clear the denominators, and then you'll plug in whatever makes these factors 0. That's how I'm choosing these numbers. I knew to plug in -1 for x because this factor and this factor are 0 when you make x equal to -1. I knew to plug -2 in for x because this factor and this factor are 0 when you plug in -2. So I'm plugging in numbers that make as many of these factors drop out at once as possible. That will allow me to read off the value of the coefficient attached to the remaining factor. And because of the way the algebra works, you'll always have one guy left when you plug in something that makes the other guys 0. So when I plug in -1, the factor that doesn't have an x plus 1 will survive, and that will allow me to read off the coefficient b. When I plug in -2, the factor that doesn't have an x plus 2 will survive, so I know that that will allow me to read off the coefficient c. There is no number I can plug in for x that will make everybody else 0 but not make this 0. Anything that makes this guy 0 also makes this guy 0. Anything that makes this guy 0 also makes this guy 0. So I cannot use the Heaviside trick to recover the coefficient a. So this is an answer to Nick's earlier question. Does this always work? No, not always. So what do we do from here? Well, I've got a method that works otherwise. It's the shit we were doing last week. But before I jump back in and do that, I should update this equation because I've got the value of b and c. So now we update the expression star with the information we got from Heaviside. That will become x squared plus x plus 1 equals a times x plus 1 times x plus 2. And I don't know what a is yet, so I can't do anything there. But I know that b is 1, so this will just be plus 1 times x plus 2. And I know that c is 3, so this will be plus 3 times x plus 1 squared. I'll call this 2 star. And I could multiply everything out, collect like terms, and set up a linear system. And if you have more than one coefficient left to solve for, that's probably the game. But remember, I can plug anything I want in for x. And Maggie had a suggestion earlier in her 8:15 comment, well, maybe we should try plugging in 0 for x. I could plug in the square root of 2 for x. I could plug in pi for x. We could plug in whatever the fuck we want for x. But maybe there are some other numbers that while they're not as nice as plugging in -1 and -2, are still kind of nice. So what happens if I plug in zero to 2 star? Well, 0 squared plus 0 plus 1 is 1. 0 times 1 times 0 times 2, that's a times 1 times 2, plus 0 plus 2 is 2, plus 3 times 0 plus 1 squared. And since we've already figured out the coefficients b and c, this expression has only a's, which means I can solve it for a. So let's simplify. This is the same as saying 1 equals 2a plus what? Well, this is 2, this is 3, so 2a plus 5, which implies that 2a, subtract this over, is equal to -4, which implies that a has to be -2. So I never set up or solved a linear system. The Heaviside trick allows me to recover 2 of the 3 coefficients immediately. And the remaining coefficient I could figure out by plugging in some other numbers to the equation star. But first I had to update the equation star with the information I got from Heaviside. Now I can go back and finish the problem. Therefore, the integral from 0 to 4 of x squared plus x plus 1 over x plus 1 squared times x plus 2 dx is equal to a, which is, so -2 times the integral of dx over x plus 1 plus b, which is 1 over times the integral of dx over x plus 1 squared plus c, which is 3 times the integral of dx over x plus 2. So I'm just taking the coefficients that I had and I'm using them to expand this function, which means I can expand this integral. Of course, the integrals are all running from 0 to 4. I'm doing this because I know that a is -2, b is 1, and c is 3. So from this line to this line is not anything weird. I can cover this so that the workflow looks a little more reasonable there. Everybody see how this is working? That's tasting a little toasty. All right, and from here it's trivial again. All right, each of these guys requires a little u sub. This would be like z equals x plus 1, w equals x plus 1, v equals x plus 2. The 3 substitutions here. When x is 0, z will be 1. And when x is 4, z will be 5. And this substitution I actually employ in both of these integrals. This guy here, so I'll use the same symbols in each of those. And in this guy, I'll use the substitution w equals x plus 2. dw is dx. And I also need to change his bounds. The lower bound 0 will go to 2. The upper bound 4 will go to 6. So I get negative 2 times the integral from 1 to 5, 1 over z dz, or dz over z. That's my first integral, plus integral 1 to 5 dz over z squared. That's the second integral. And then the third integral we'll have here plus 3 times the integral from 2 to 6 of dw over w. You might choose to use a different variable for this and for this, but since I'm making the same substitution in each, I'll go ahead and use the same variable. This guy, I'm using a different substitution, so I have to use a different variable. But the upshot is, I'll get negative 2 times the natural log of 5 minus the natural log of 1 from my first integral, plus here the antiderivative for z to the negative 2 is negative 1 over z. So this will be negative 1/5 minus negative 1 over 1. And then the last guy is also going to be a natural log. It'll be the natural log of 6 minus the natural log of 2. So I'm kind of combining the antiderivative step and the evaluation step here because we're so familiar with these antiderivatives. We know these guys. All right, we've done a million times the integral of dz over z. We've done a million times the integral of dz over z squared. You may want to write it out. You might want to write that this is ln absolute value z evaluated from 1 to 5. You may want to write this is negative 1 over z evaluated from 1 to 5. And you may want to write that this is the ln of absolute value w from 2 to 6. But I'm just jumping to this because I think it's fairly clear where we're going. Not much else to do here, lads and ladies. This is 0, the natural log of 1. We know that. We can combine some other like terms if we wanted to. This is 1 minus 1/5. And this is 3 ln 6 minus 3 ln 2. If there's anything to do here, it's combining these. You could also combine all the logs into one term if you really wanted to. 1 minus 1/5 is 4/5. But I would be perfectly happy with it like this. Okay, so at the end of class last Friday, we solved one problem like this, where the degree of the denominator was 3. And you may recall, it took us about 15 minutes because we had to go through just the PFD, right? Forget the integrals. Just the PFD took us like 15 minutes because we had to set up a 3x3 linear system, solve it using row operations, and I could feel the tension. All right, even though we're not together in a room, like it's sometimes a little bit obvious when things are not feeling good from your end. And I get that because the row operations and matrix methods and all that stuff from pre-calculus probably is a little bit rusty. And even if it's not rusty, most of us don't like it. personally. I have a lot of love for linear algebra and matrices, but I still don't enjoy just straight row reducing matrices. It's not fun. And row reducing a linear system is similarly just not fun. So the Heaviside trick, good trick. Now there's a case that we haven't confronted yet, and that's how to handle irreducible quadratic factors in the denominator. So I'll pause here for a second. If you have any questions about this problem, I'd like to address those. Yeah, the theory behind matrices is very cool. Learning about matrix algebra and linear algebra in general, very, very cool. But the process of working with it, not so much fun. I would have to say I agree, Nicholas. Questions on this? Okay, then. So what about those irreducible quadratic factors? There is one of these in your homework, but I wanted to be gentle, so there's just one. And I don't want to spoil it for you because I feel like it's an important problem. So instead of showing you exactly how to do this one, I'm going to do something a little bit different. So number 17, if you want to make a note, number 17 will require something very similar to what I'm about to show you. I'll grab the example from the textbook because I don't want the arithmetic to get out of control. Somewhere in here, I'm sure we have a quadratic. Okay, we'll do this one. Let me write it down. There we go. So the degree of the top is 2, the degree of the bottom is 3. It is a proper rational function, so I am capable of running PFD on this. Before I do that, I'm going to rewrite this with the denominator factored. So if they don't give it to you with the denominator already factored, of course, you're going to need to factor the downstairs. Begin. I can pull an x out there, and what's left is x squared plus 4. And x squared plus 4 is an irreducible quadratic factor. The roots of this quadratic are not real numbers, right? That's how you can check if a quadratic is irreducible. Thankfully, there's no such thing as an irreducible cubic or an irreducible quartic or anything like that. Every polynomial can be factored into linear factors and irreducible quadratic factors. If you're willing to work with complex numbers, this can even be factored further as x minus 2i times x plus 2i. But for us, in the calculus sequence, we really don't mess with complex numbers. We like to keep everything in terms of real numbers. So from here, I will set up my PFD following the rules associated with irreducible quadratics. Remember what that PFD Bible says. First, I have this simple non-repeated linear term he will contribute one term to the PFD setup. But then I have this irreducible quadratic factor. He will contribute a term to the PFD setup that looks like this. I have to allow for all possible expressions that could have contributed this to the downstairs. Since this is a quadratic and I'm allowing for all possible proper rational functions that could have been added up to contribute this factor, I have to allow for the possibility that the numerator is linear. The degree here is 1. So the degree upstairs in any proper rational function where this is the only thing in the denominator has to be 0, which means that the numerator has to just be a constant. But the degree here is 2. So if I'm asking what are all possible proper rational functions that could have had this as a downstairs, that's not just a constant, that's any linear function, any degree 1. So remember, irreducible quadratic factors get linear numerators, not constant numerators in the PFD expansion. So this is my setup. And just like always, I'm going to multiply through by the denominator. I'm going to cross multiply to kill all the fractions. So my left-hand side will become 2x squared minus x plus 4. And my right-hand side, when I multiply this by x times x squared plus 4, the x's will cancel, and I'll just get a times x squared plus 4 plus, here, remember your parentheses. These are fractions are grouping symbols. I have to think of it like that. So this is going to be paren bx plus c times the x squared plus 4's will cancel, and I just get an x. I could now multiply everything out on the right-hand side, collect up the coefficients of x, x squared, and constant terms, and set them equal to -1, 2, and 4, respectively. But instead, I'm going to use the Heaviside trick to recover as much as I can. In this case, I will only be able to recover a. It's always nice to let your reader know what you're doing. That's why I write PFD here, so you know that I'm starting some partial fractions. And before you employ the Heaviside trick, go ahead and write Heaviside. That way I know what you're doing. Yeah, Maggie, go ahead.
I'll just unmute because it's easier.
Oh, I'm sorry, I cannot, let me turn up my volume. I can't quite. Okay, go ahead.
Since we have an x squared and the x squared plus 4, are we going to be able to get a term that equals 0? Oh, never mind. Wait, never mind.
Yeah, that's the problem, right? Is that there isn't anything nice to plug in to make this 0, which means I won't be able to get these guys using Heaviside. But if I plug in 0 for x, this will be 0. So these will all go away, and that will let me get the number a. So a is the only one I'll be able to get, but b and c, those will not be able to follow from this. So at x equals 0, my equation here, star, becomes 2 times 0 squared minus 0 plus 4. That's 4 on the left. Over here, I'll have a times 0 squared plus 4 plus bx plus c times 0. Oh, sorry, b times 0 plus c. Yeah. In any case, this whole apparatus here is 0 because of the 0 here. So I get 4 equals, this is just 4a. So a is 1. But there's nothing nice I can plug in that will make this guy 0. I could plug in 2i and negative 2i. I'm kind of fibbing a little bit there, but you would have to be willing to mess with complex numbers. So instead, now I update my equation star with the information that a is equal to 1, and it will become 2x squared minus x plus 4 equals 1 times x squared plus 4, that's just x squared plus 4, plus bx plus c times x. Now, unfortunately here, there's more than one variable remaining. There's more than one coefficient that I'm solving for that's left, both b and c. So even going in here and plugging in some other random number to try and solve for the remaining guys won't work. So we still have to do some linear system work. Oh, I should call this 2-star. So from here, we treat this like we were doing things last week. I multiply everything out, gather up my coefficients, set up a linear system. But having done Heaviside at the start, the linear system I'll get will be smaller because I already know the coefficient a. Right? There's only 2 unknowns in this, b and c. So let's do it. If I multiply everything out here, I'll get x squared plus 4 plus bx squared plus cx, which means 2x squared minus x plus 4 is equal to, well, let's see, x squareds, I have b plus 1 of them. X's, I have c of those. And constant terms here, I just have plus 4. So the coefficient of x squared on the left has to match the coefficient of x squared on the right. The linear term on the left has to match the linear term on the right, and the constant term on the left has to match the constant term on the right. So my linear system is 2 equals b plus 1. The coefficient here, this is negative 1x, right? So negative 1 equals c, and 4 equals 4. That's a pretty simple linear system, don't you agree? In fact, we don't need to do any row operations. Equation 1 says 2 equals b plus 1, so subtract 1 from both sides, you get 1 equals b. Equation 2 just straight up tells me that c is negative 1. So here are the 2 remaining coefficients. So the Heaviside trick still made our life substantially easier in 2 ways. First, it gave me the value of a right out of the gate. That's awesome. Second, the updated version of star was much simpler than the original version of star, right? Compare star and 2-star. This is relatively complicated. It has 3 unknowns, a, b, and c. This has 2 unknowns, just b and c. And what's more, after you combine all your like terms, we could call this 3-star if we wanted. The linear system that we're able to set up from 3-star is utterly trivial, right? There's no, you don't have to do any substitution or any elimination, no row operations, no matrices, no nothing. Super simple system. And this system, if I had constructed it from the original equation star, would not be anywhere near this simple. So the Heaviside trick, which concluded here, right, this is all of our Heaviside work, really did save us a lot of work. Now I have a, b, and c. A is 1, B was 1, and C was -1. So I can come in here and finish the problem. Therefore, the integral of the object on the left is equal to the integral of the object on the right. Now, the integral of the object on the right is not quite as trivial as the other problems we've seen because this piece is not ultra simple. It's still pretty simple. I'll show you how to do it. But before that, any questions on this procedure that we did? Going once. Going twice. All right, so the remaining integral here, I'll split into 3 pieces. Integral dx over x plus. This fraction I can split up as x over x squared plus 4 minus 1 over x squared plus 4, and I'll do that. X over x squared plus 4 dx minus integral 1 over x squared plus 4 dx. Easy. Easy question mark. How do I do the middle integral? Good. So here I will make the substitution z equals x squared plus 4. dz is 2x dx, so I'll get a factor of 1/2 out here, and then I'll end up with the integral of 1 over z dz. What about here? What do I do in the third integral? Good, trig sub. Now, this guy is in a special form, and we will use trig sub, but I encourage you to look for patterns in this integral because I could tell you right now the value of this integral. And I think most Calc 2 students after finishing exam 1 could tell you right away what this integral is because you'll have seen it so many times. 1 over x squared plus a squared will always come out to a certain thing, but it is trig sub. If you don't know what it is right away, the x squared plus 4 tells you to substitute x equals 2 tangent theta. It's trig sub. dx is 2 secant squared theta d theta. So here we go. First piece is natural log x, natural log absolute value x, plus. Second piece is 1/2 integral 1 over z dz, minus. Third piece is 2 secant squared theta over 4, I'll write it like this, 2 tangent theta all squared plus 4 d theta, right? The secant squared coming from the differential. So I get natural log absolute x plus 1/2 natural log absolute z minus integral 2 secant squared theta over 4 tan squared theta plus 4 d theta. So that's natural log absolute x plus 1/2 natural log absolute z was x squared plus 4 minus integral 2 secant squared theta over, I can factor a 4 out from the denominator here, and I'll get tan squared plus 1. And tan squared plus 1 is secant squared. So this is log absolute x plus 1/2 log absolute x squared plus 4 minus 2 over 4 is 1/2. And I get secant squared theta over secant squared theta because tan squared plus 1 is secant squared theta. So those cancel perfectly. And we just have there the integral of 1 d theta. So this is ln absolute x plus 1/2 ln absolute x squared plus 4 minus 1/2 integral d theta. So that's ln abs x plus 1/2 ln abs x squared plus 4 minus 1/2 theta plus a constant. And then we have to come back to our substitution. X equals 2 tan theta implies tan theta equals x over 2 implies theta is the inverse tangent of x over 2. So my final answer here is natural log absolute x plus 1/2 natural log absolute x squared plus 4 minus 1/2 inverse tangent of x over 2 plus c. And that's it. You guys have now seen all the different things that you need to do with partial fractions. The trig sub is important. Your exam will require you to solve some trig sub problems. But the trig sub here could have been skipped, if I'm honest. So in parting, I'm going to leave you with a suggestion. Let A be an arbitrary constant. Let's see, where can I drop this so that it won't get in the way? How about over here? I think at this point, we all know what that left-hand side, left part was doing. I would like you guys to prove that for any number A, the integral of 1 over x squared plus a squared dx always comes out to 1 over a times the inverse tangent of x over a plus c. So in our problem here, a was 2. The maneuver is a trig sub thing. It's not hard, but on an exam, do you want to have to do all of this? Or would you like to just go from the line up here to this piece right away? I know what I would rather do. PFD is on exam 1, yep. So the cutoff for exam 1 material was last Friday, and we did finish section 7.4 last Friday. Today, I'm just showing you some tricks to do those things faster. So exam 1 is going to cover everything from U sub up to partial fractions. Exam 1 is all the integration techniques. Also volumes, average value. Those things are fair game for exam 1 as well. So some cylindrical shells or some disc washer stuff could certainly be on exam 1. If you remember, I actually gave you a warning about a particular problem that is guaranteed to be on exam 1 in one flavor or another, having to do with volumes. I'm glad you asked that, Nick. Yeah, so we talked about this a little bit last week. Exam 1 was supposed to be this Friday, right? But Santa Fe, in their infinite wisdom, is closed this Friday for UF's homecoming, even though UF isn't closed for UF's homecoming. So yeah, Monday. Monday is going to be the exam. So next class on Wednesday, I will be showing you guys some material that's not on exam 1. All right, we're going to cover a couple sections in the textbook that are not super heavy sections. They're actually fairly light. And then this Friday we are off. So no, I'm not allowed to have a class on Friday, unfortunately, because this is a virtual section. I'm not allowed to have class on a day when the college is closed. So this Wednesday, I'm going to cover a little bit of new stuff. Next Monday, a little bit more new stuff. Next Wednesday, review for test. Next Friday, the test itself. But the cutoff for the exam material, you could think of as being last Friday or today, if you prefer. You know, this stuff will certainly be on there. All right. So the study guide is up. I intended to get it up last Friday. I'm sorry, I forgot. We had a busy weekend up here. But the study guide is up. I posted it yesterday morning, so that's there. Please be working on that. The sooner you can get that submitted, the sooner I can go in and start giving you feedback. You want that feedback for the exam. Oh, thank you guys. That's very sweet. So please get working on that study guide. The homework I'm going to extend to be due next Monday rather than this Friday. That way you can continue playing with that until the test also. And make sure you're comfortable integrating anything and everything. The best way to prepare for this test, come in here to section 7.5. You gotta know these. These are the basics, right? And you'll notice that number 17 is the formula I asked you to prove. The bottom two here, I don't necessarily recommend that you memorize, but you can. But then section 7.5 doesn't have anything new. It's all stuff that we've done before. There's no new methods. But they show you how to attack problems. They discuss how to attack problems when you can't infer from the section number how to use what method. So look through section 7.5, make sure you can solve all the problems in here. All right, there's lots and lots of problems. So I would come through, if you finish the homework and the study guide and you want more practice, just come in here and knock out all of 7.5. Just blast through these problems. And if you get stuck on anything, come see me in office hours or send me a Canvas message and I will work with you guys as much as I can. So the test is next Monday. It would have been this Friday, but instead it is next Monday, right? So, oh yeah, so I apologize then. What I said a second ago, this Wednesday, yeah, sorry. So I was talking there like we had a week between now and the test. We don't. So this Wednesday, I'll do the review. Yeah, I won't drop any new material on you guys between now and the test because we're closed this Friday. So next class will be a review. Then we're off this Friday. Then the test is next Monday. That's how we're doing it. I'm sorry, that was confusing, wasn't it? So between now and the test, make sure you finish the homework, make sure you finish the study guide. Then if you want to practice more, section 7.5, full of good problems. I'll review during our next class, which is Wednesday, then we're off on Friday, and then the test will be during class time on Monday. I'm going to post some instructions under a Canvas announcement for the exam. Make sure you read those instructions and make sure you follow them exactly on the test day. I strongly recommend you download an app like Cam Scanner, or if you have an iPhone, play around with the Notes app. Make sure you can do the following two things. Make sure you can scan something in a way that it is legible as a PDF. Gotta be PDF. And then make sure that you can save that on your phone or save that on your laptop as a PDF and upload it to Canvas because you'll be required to do that with your written work. So with the study guide, think of that as a trial run for how you're gonna upload your written work for the test. Okay? All right, that's it guys, stay safe, have a good afternoon. I will see you on Wednesday when we review for the test.